Hello, everyone. Thank you for joining us today. If you don't know me, my name is Mitchell. I'm the field engineer for the government down in Southern California and parts of Arizona. Today, I am joined by Keysight's greatest application engineer on either side of the Mississippi, Jason Gamola. I'll let Jason do an introduction for himself.
Hello, everyone. My name is Jason Gamola. I'm the RF and microwave applications engineer for the San Diego and Tucson region, specializing in RF and microwave for aerospace and defense. My background is mostly in radar systems, design, building, and testing all different types of radar systems. And my usage of Keysight equipment is what brought me to this role. They brought me on about 2 years ago almost. So I'm happy to be with you here today, and we'll get into it. We're going to do kind of a compressed webinar. Let me share my screen.
That's right. You guys are very lucky to be presented to by Jason. So like Jason said, you guys know the drill. Today, we're going to do connector care and basis of network analysis. Before we jump into that, though, real quick, we're going to do a quick warm-up. I'm going to put a poll up, and it's going to contain a very controversial question. You guys can choose the best answer that applies to you. Okay. So we're just doing this for two reasons. One, to warm you guys up, and two, this may or may not be used to settle a dispute I'm having. But so does pineapple belong on pizza? Yes, no, indifferent, and don't worry. It's all anonymous, so there's a judgment-free zone here. So I'll let you guys vote
Relating
in.
to pizza, when the world opens up, we can do these classes in person and we can bring pizza. So this question may be more relevant.
That's right. This we're definitely trying to compress a lot of information into something, and I'll mention this at the end. I'll mention it right now too. But if you guys want to see more, just there's gonna be an evaluation at the end. You can put some topics that you might want to look at or you might want to look more into, and me and Jason come out there and do some of that stuff. I'm gonna go ahead and close the poll, and it looks like majority of us said no. It's an interesting decision. I may or may not agree with that. I won't let you guys know now. Maybe if we see each other in person, I'll let you know my answer. But thank you guys so much. So it looks like the polls are working, and I'll let Jason take the floor.
Okay. So you guys can see that, I'm assuming. This is the rough agenda we're going to cover. We're going to keep it pretty flexible, pretty open. I'll try to keep it light and fluffy. I won't dive too deeply into the equations. Apologize for the muffled mask noises. I'm in the office today, and those are the rules. So we have a question section at the end of each subsection where we can open the mics and ask questions. Additionally, there's a chat function in the platform where you can type your questions in, and Middle's going to monitor those questions, and he's going to make the assessment whether he can answer them quickly on the fly, or if they're relevant, we can talk about them during. I don't mind being interrupted for those, or we'll save it for the end of the section. All right, so I think that's the intro. We probably have enough people on board to get going, so let's do it. This is the extensive list of what we're going to cover, or what we're going to breeze over with connector care. Usually this is done in a full hour face-to-face presentation where I actually hand out the different connectors and you can see what they look like and see what a good one and what a bad one looks like. But since we're doing it remotely, we're just going to go through, we'll do the brief version. But why do we care? Why is this important? This is kind of what the takeaway is. Now, one of the connectors in your RF test system is probably on the low end of the cost point. It's a relatively cheap component given the cost of your device center test and your measurement equipment. So the tendency is that people typically just breeze right over that and ignore how important these little components can be, and the effect of what happens when they're not in good shape. So let's run through a scenario that is a possible outcome if you have a bad connector. So here you have an older PNAX 4-port unit, pretty expensive piece of test equipment, very precise and high precision. And you take a high precision cable, you know, fancy phase stable cable, and you don't notice that the pin on this cable is broken, or the female portion, the connector is broken, and you connect this into your PNAX, and it feels a little weird, but you just give it a little extra oomph on the connection, and then you go on with your day. So the first thing you'll notice is that you get bad measurement errors. So this will, give you not only bad measurements, but it'll also damage the connector on the PNAX. So then next time you use that PNAX, that port, you'll be getting, the errors will propagate to the measurement unit. And then you don't figure out what's going on, and you move on with life. Things look a little weird, so you connect another cable back to that port. And now you've just ruined 2 cables, and you still have the ruined port of your PNAX. So now you can see where this is going, and how those problems can cascade. Now, if you have to, once you do figure that out and you get it repaired, you're talking replacement or repair costs for each of those ports. And if you know anything about the PNAX or anything about high precision test cables, you know none of them are cheap. So there's the actual cost of the replacement and the repair, and then there's also the time cost. And also, I've learned working with the Air Force and the Navy that repair time, 15 days would be pretty optimistic. It usually doesn't work that quickly. There's also lots of paperwork involved, which is painful. So one little connector can cause all of these problems and costs and delays. So
with that being said, I kind of want to gauge what everyone's experience is with connectors. So I'm going to launch a quick poll real quick just to gauge your guys' experience. This way Jason can have an idea of what details to mention.
yeah, so the targeted audience for this talk is kind of entry level to new engineers, also people maybe transitioning to a lab who haven't been in a lab in a while, or people who just kind of want to learn some finer points, or want a medium to ask questions and learn more. I've been doing this I've been in the industry for almost 15 years now, and I still, still plenty to learn about all of these subjects. And like I mentioned before, if there's any particular area that we want to dive deeper into, we can get to that.
Yeah.
Each one of these slides could probably be turned into its own entire webinar if we dive deeply enough.
Yeah. So it looks like most of us here have had a moderate level of experience, just a few years, and then some of us have little experience or are just starting out.
And somebody just wanted something to do during lunch. That's cool. I do the same thing. Now here's another example of the compounding connector problem. If you have a broken connector that is bad enough to cause measurement error, but not bad enough to immediately stand out. It's just, let's say, one of the little fins on the female connector, on the receiving side of the female connector, is broken, and it just makes your measurement a little bit off. So you hook up your device under test, and it runs for 3 hours, and it just looks a little bit funky. So then you have to do your diagnostics. That even though your device under test is good, you spend an hour doing diagnostics and rerunning some tests and trying to figure it out. And then so you run it again another 3 hours, and then you troubleshoot an hour, then you consult with your team, more hours, and then this starts over. And so this is, you know, another reason why it's important to just pay some attention to the quality and care of your connectors. Another example, which I'm sure everybody's seen at least once in the lab, where your cable's 4 inches too short to reach to the next leg of the chain, and you can't figure out how to make it work. So somebody says, "Oh, I have these adapters. We can just plug them all together and get that 4 inches." Or you don't have the correct gender of your adapter, so you have to route through your entire bin of connectors and come up with this monstrosity. And somebody says, "It'll work. I can see a signal through it." But you should know what you're doing to your measurement when you do this. And it'll work, but how well will it work? That's the question. You should know that in this case, when you're cascading all these connectors together, the most obvious thing is you're limited by your lowest performance frequency connector. So in this case, it'd be this BNC, which is only spec to 4 gigs. So you could have a 34 gigahertz signal in, and each one of these connectors is going to successively degrade your signal. And you're only spec to about 4 gigs at that point. The next thing that may not be so obvious is what this does to your measurement uncertainty. With each one of these connections, there's a reflection amplitude mismatch and a phase mismatch. And to do your uncertainty analysis, you have to cascade the mismatch for each individual connector. So when you do the math and add all this up for each of these 4 connectors, so you have a tolerance associated with each one, and you sum them up, you can get plus or minus 3 dB amplitude variation just by using this monstrosity, and almost a 23 degree phase variation just by using this shortcut. So the moral of the story is, let's not do that. Now let's talk a little bit about the different types of connectors. There's a huge array, huge variety of connectors, and a lot of them, there's different terms for the same connector. There's proprietary terms, and lots of interchangeable ones, and then ones that are close but not quite interchangeable. Also within that, there's different grades of connectors. Let me see the ones that ship with the equipment. They look a little different than the ones you find lying around on benches. So the best case option is highest grade precision are the metrology grade ones. These are obviously the most expensive, the calibration grade, and the highest precision in the manufacturing. They have the tightest tolerances, and they provide the most repeatable measurements. On the other end of the spectrum is the cheapest production grade or general purpose. These are meant for low number of connection cycles. They're not built to be screwed and unscrewed repeatedly all day long every day and provide a repeatable measurement. Every time you use it, you're degrading it. They're often plated, and the plating is thin and wears off quickly and easily. And they're often the source of many issues in the troubleshooting. In the middle is the instrument grade, which is a good compromise between the two. Now there's a huge range in the cost of these. Here's just an example showing some of them. On the cheaper end, cables and adapters can be $15 for these lower end SMA cables. Now on the higher end, if you're 1 millimeter adapter for this would be for like a 110 gigahertz measurement, can be $3,000. So just another reason why we have to take care of these things and pay attention to some of the important notes of this talk and on how to do so. Now, if we're looking at what's what with the connectors, some of the more common ones, these are for the RF and microwave world. These are the ones you'll see most often. SMA, they're rated up to 24 gigahertz, but that's manufacturer specific. 3.5 millimeter can go a little higher, and you see the difference here. The white is actually the Teflon dielectric, which separates the center conductor from the outer conductor. And when we move to the 3.5 millimeter connector, we use an air dielectric. So this is a little more precisely controlled and less temperature variant. If we have to go to 40 gigahertz, we switch cable connectors and threading to the 292 connector, which goes up to 40. Now these three are all in the same series and will actually are often used interchangeably, but people don't know the difference. Previously, the old timers will tell you never to mate an SMA with a 3.5. And the reason is the SMA connectors used to not be controlled precisely in terms by specification. So this pin depth was variable and also the pin diameter was variable. So you would take this male pin and plug it into a 3.5 female and it would destroy this female receiving section by expanding it to the point where it couldn't return. Now, so much that's not a problem. So as long as you make sure that it is not a 40-year-old SMA connector and give it an inspection, it will mate safely with a 3.5 and even a 292 connector. Now this next slide goes over some of the other connectors and what they mate with. And we'll get into where these measurements actually are taken from on the next slides. But just for now, I wanted to cover the different series of the connectors. Now, up from the SMA series, we have the 2.4 up to 50 gigahertz that will not mate with a SMA or 3.5, but it will mate with the 185 higher 70 gigahertz connector. And then if you go up to 110 gigahertz, we need the 1 millimeter connector. Whew. Okay. Just a little bit of equations, but I promise not to go too deeply. The measurement, as I said, comes from the relationship of the outer diameter. It's the inner diameter of the outer conductor, is what I meant to say, and that defines the characteristic impedance of that cable. So a brief, shortened equation for that is the ratio of the two diameters times 60 divided by the dielectric constant of the natural log of the ratios times 60 divided by the dielectric constant of the dielectric. So in the case of an N-type connector, we have a 7 millimeter outer conductor. Inner diameter of the outer conductor is 7 millimeter. So that's where that connector series comes from. And then the next one would be the 3.5 for the SMA series, and so on. Now the other equation that's governed by this connector geometry is the frequency coverage. So in the case of the SMA, we use it's the ratio of the two that determines the frequency coverage. And this equation here, 120 divided by your outer diameter, will give you roughly your highest frequency. And like I said before, there's a big range with some of them. SMA is the main culprit, where the manufacturer can specify SMA cables only good up to 18 gigahertz, and some of them go up to 26.5 or 27 gigahertz based on how precise their machining tolerance was and how much variability they have in their process. One other thing you'll occasionally come across, although I've only heard of this in my experience, I've never actually seen one, is 75 ohm connectors. So these are something to be aware of when you're digging through somebody else's cabinet for a mating connector. In certain cases, the common example is cable TV. They use a characteristic impedance connector of 75 ohms, and they're denoted with this stripe in the knurl or the tightening barrel area of the connector. Okay, moving right along. This chart shows the trade-offs between power handling and frequency. So these are just important considerations if you're doing your connector design or system design and which connectors you use. Oh, okay, this is a close-up photo of what you should be looking for in a connector. On the left side is these are called slotted connectors. You can see these fingers that go along the coaxial dimension of the connector. They're actually, in this case, there's 6 fingers. And these are what make physical contact with the male pin when the connectors are screwed together. And so this is what you want to look for when you take a connector and do your visual inspection, is you want to make sure that if you have a slotted connector, which are most production grade and instrument grade connectors are slotted, take a look down the receiving end of the female connector and make sure that all the pins are intact. If you see something like this, where you can see a slight bend of the finger, and just imagine what happens if you were to stick in the male connector. That pin is going to get broken off. It may get folded in there, which will cause a short. Or worse, just a loose connection, and that'll be the next step. Is that it'll become a missing connection, missing finger. And then once they're all broken off, then you'll just have no fingers in the connection at all. How does that happen? Things like this, throwing all your connectors in a metal tin. That's definitely on the do not do list. And putting the connectors in a tin itself is not a crime, but mixing them with all of the screws and debris that comes from all of the connectors being tossed around and the plating scratching, and that winds its way into the dielectric, and then it gets screwed into the mating surface of the connectors. So one of the ways you avoid that is using dust caps whenever possible, and whenever throwing them into a bin, make sure they have a dust cap on, and keeping your connectors clean.
I'm curious if anyone in the crowd, I'm launching a quick poll here, have bad connectors ever affected any of your testing in your lab or anything like that? I'm curious what the audience might have. Yeah, awesome. Yeah, it looks like 72% of us have. Yeah, so and using those results, we see how important just this topic is to talk about.
Yeah, and in my experience, that's not the fun type of troubleshooting. There's troubleshooting in the lab when you get to the bottom of a problem and you can identify the failure, and when you spend all that time and you realize it's just a connector that you didn't carefully use, it's not a rewarding type of situation. So how do we prevent that? Like I said, inspecting the connectors, looking for debris. Obviously, don't use a broken connector. Do everyone a favor, just throw it out. And also, when you do the inspection, check for deformed threads. I think we have a poll question that may relate to how threads get deformed, if you want to launch that one, if that's possible. So if you have a stuck connector, this is one that everyone has seen in their lab at one time or another. and you do it wrong, you can damage lots of things, including the threads of the connector. Um, and there's lots of fun ways to do it wrong. But using a wrench or using the soft draw pliers is definitely the right way to do it. So keeping your connectors clean, we just want to brush them off with compressed air, using a lint-free swab to touch not the dielectric, but just the threads of the outer connector. And in general, unless you absolutely have to, stay away from the inside of the connector. And use the minimum amount of alcohol and make sure you allow it to dry, and use a high-grade alcohol so it doesn't leave a film on the surface. Obviously, don't use your high-pressure blaster. Don't use a scrubby connector or a scrubby abrasive pad, and don't saturate the connectors. And don't just get in there with the Q-tip and go crazy and apply lateral force to your center pin of your $3,000 1mm connector. There's a proper way to make these connections when you're actually putting them together, and this is important. I think it's often glossed over. You can see from this animation what it looks like in a cross section, how these things actually go together. Now, ordinarily, you would keep your female end of the connector on the right stable, and you would actually move the male connector into the female and hold the female connector stable, and just turn the nut on the male end of the connector. And what this does is rotates this section of the connector and allows the pin to stay stable, so you're not twisting the pin, and also you're not twisting the female end of the cable. There's another cross section of that. One other common lab practice that will save you a lot of headache is to use connector savers. Connector savers can be just typical, just simple adapters as an interface between your test connection, your test equipment, and your connection. And this will allow you to have an intermediate replaceable part that you can use till it wears out and then replace it without actually having to repair your test equipment port. I jumped the gun on this one. I wanted to get the poll in there before I gave you guys the answer, but don't use this because it will ruin your connectors. Soft jaw pliers are the right answer. One quick thing I want to touch on is torque wrench, and the correct way to use a torque wrench. If you see torque wrench like this, they'll have a line here. You hold behind the line. You can kind of do it lightly with 2 fingers, and you make the connection on the male section of the nut. And then as soon as this joint here bends or breaks, you stop and you don't go any further. That's the correct way to do this. If you have to hold the other side, you use a second wrench and just keep it static and don't move it. And then you rotate the torque wrench until it breaks. Don't turn both wrenches because that can apply some lateral force on the center pin. Like I said, grab it here and push until it's just broken. You don't need to go all the way around. It's no longer a calibrated measurement if you do that. Here are the common torque values, but you'll just have to look this up for your specific situation based on your connector type. And just want to point out that the torque value for an SMA is actually lower than the torque value for a 3.5, even though sometimes they're used interchangeably. And the reason is that too much torque on an SMA can actually damage or make a poor connection. We'll jump through that. And this becomes increasingly important when you're in 1mm connectors because they're easy to break and way more expensive. So we'll sum it up real quick because we have a lot more to get to. So don't use pliers, use alcohol and lint-free swabs. Don't use a higher frequency connector than you need because it's doesn't help you. It just adds complexity and expense. One thing I didn't mention earlier is never use a calibration kit as an adapter, ever. This will get you in trouble. Use a torque wrench anytime you require a precise measurement. Obviously, righty-tighty, lefty-loosey. And don't force anything. If a connector doesn't go together, if it's not going together, there's probably a reason. You probably have the wrong connector or the connector's damaged. So there would never be a situation where you need to force it, because that's how you break things. Here's some links just included in the overall presentation. Microwaves 101 is a really entertaining resource that has some really good information on this if you want more than what's been included here. I think that's it for this presentation. Is there any questions so far? That's there.
So there's none in the chat, but if you guys have a question, feel free to come off mute and ask it now.
Okay, let me just queue up the next one while that's going on. So that I can close. Network analysis basics. Okay. Now, to put that there and swap. Okay, so got caught up a little bit there. Now we're going to transition into network analysis basics, and this one is definitely a subject that could be broken up into many different parts. And to do it in 30 minutes or less is going to be just a brief overview of network analysis. We won't be able to dive into things too deeply, but there's always room for future topics, so please let us know. So know that there are entire textbooks written on just network analysis. And the one I continually reference from Dr. Joel Dunsmore's 850 pages, I think. So we won't cover that in 30 minutes.
We have a question from James. Jason, I don't know if you see that. What is your recommendation on labels on these connectors?
Oh, yeah, so I don't have it up, but there's a company called Maori that actually does color-coded connectors. Excuse me. And if you look into that, I think that's a really awesome idea, and I wish everyone in the world did that. That'd be my recommendation, is if you could either use their color code, which I think they're trying to make an effort to standardize and bring to the greater connector world. The color coding system, I think it's actually based on the resistor color coding scheme somewhat, but it color codes which connectors and adapters, so you can just briefly take a quick look at it. You don't have to look down the barrel of a connector and try to figure out if it's a 2.4 or a 3.5 connector. I think it's yellow for 2.4, and then you have a yellow stripe on the connector and a yellow stripe on the torque wrench, and that way you know that the torque wrench is suitable for that connector, and you know that yellow mates with whatever the next color is on the list. So the color coding scheme is listed on the Maori website. It's also listed on microwaves101.com too. So if you had to come up with a color coding scheme from scratch, there's one to base it on. Does that answer the question? Or if it doesn't answer the question, send me a follow-up question and I'll dive into that. Okay, moving into network analysis basics. First question is why? What do we want to measure? And the answer is everything in the RF chain can be broken apart into multiple building blocks and characterized individually. So the network analysis will allow us to do that and then quantify and save data, simulate each of these parameters within your chain and at each section in your chain. So we can independently measure power. We can vary the power, and we can measure it over frequency for at each of these sections in the transmitter receive chain. So this gives us, the network analysis will give us both magnitude and phase, which can allow us to do the characterization of the linear networks, allow us to find the necessary impedance to do impedance matching within circuits, which is necessary for power transfer. This will allow us to simulate in a realistic manner using ADS or whatever simulation tool you guys might use, and then take the real world values and interchange them with the simulation, and take the simulation values and stick them into the network analysis measurement. You can do time domain, doing an FFT of the frequency measurement. We can translate that to time and actually do fault location. And we can do corrections. And with magnitude and phase combining to provide a vector signal, we can do vector error correction, which is going to give you the highest measurement accuracy. And also getting more advanced, we can do nonlinear characterizations using X parameters or pre-distortion. Do a quick overview of transmission lines. The classic example of transmitting energy is the light wave example. So I lost my pointer. On the left side, we have a light wave. The incident wave is in we'll call it the forward direction, and it interacts with a device. In this case, in the light wave example, it's a lens. Now, depending on the properties of this lens, if it's anything less than completely perfect, some of that energy will be reflected, and some of that energy will be transmitted. And the analogy for network analysis is RF network analysis is the same. So if we have a device under test, whether it's a filter or an amplifier, some of that energy is transmitted through and some of it's reflected. And the entire strength of network analysis is measuring the ratio of the incident wave to the reflected wave and the incident wave to the transmitted wave. So once we know that, we can characterize the lens or the device under test in the middle. With high frequency measurements, just as it relates to this, the important takeaway is that you can't just take a measurement of voltage of a high frequency signal on a line with a multimeter. And the reason for that is when the wavelengths get smaller or much smaller than the transmission medium, which would be the coax in this case, there's multiple modes occurring within the transmission medium. So the voltage actually varies with distance as the signal is transmitted along the line. If it were just a low frequency wire, a low frequency signal, the voltage would be the same across the whole wire. And that becomes important in your different transmission medium. Here we're going to focus on coax. I'll just zip through there. Just some terminology we need in order to build how a network analyzer works. We discussed previously the incident and transmitted waves and the reflected waves. Now those waves, the measurements of those waves are done with receivers, and we use two different notations. The blue notation is the lowercase, the A receiver, the B receiver, so A1 and B1, B2, and that's often notated in older textbooks. The newer notation that Keysight uses now in the block diagrams and documentation is the capital. So you have an R1 receiver and an A receiver, and then the B and R2. And that'll become important as we transition to higher port count VNAs. So briefly cover that later in a block diagram. And here just showing some of the measurements and some of the terminology associated with that. Like I mentioned, it's about network analysis is about the ratios of those incident, reflected, and transmitted waves. And so as we take that, from there we can discern the same measurement in different forms. So VISWAR, return loss, or S parameters, S11 and S22 are the common ones. But they're actually a measurement of the reflection coefficient, and that's where it originates mathematically. And in the forward direction, different ratio, but same idea. So this is where you get your gain and your loss, or your S parameters, and then phase and group delay, they're all derivative of the transmission coefficients. Whew. Okay, we'll come back to this one if we have time, but this is, like I said, just different forms of the ratios and the mathematical breakdowns of those. The only thing I want to point out here is just the relationship between the reflection coefficient, return loss, and VISWAR. If you have no reflection or a perfect transmission, your reflection coefficient is 0, your return loss is negative infinity, your VISWAR is 1, or the worst case scenario where you have an open or full reflection, so is on this side where you have 1, 0, and infinity. So just note that as you go from, let's say, return loss to VISWAR, the infinity is on the other end, and you can see the relationship here. I won't dwell too much on that before I put everyone to sleep. Okay, so now we want to talk about how a network analyzer actually does the measurement. So first, if we start off with our device under test, and we don't know what it is, and we want to inject a signal into it, so we have a source, and we connect it up to the device under test. But in order to know what we're putting into it, we want to measure off some of that signal from the source and save it and send it to a receiver to measure. So we do that with a coupler. And if you can see in this, the notation of the coupler, the arrow signals coming from this direction, and the arrow directs the energy to the receiver. And the energy coming in the reverse direction is sent to a termination. So in this case, it'd be a 50 ohm termination because we're working in a 50 ohm system. So the only signals being propagated into the device under test, and a small portion of that signal is being picked off and sent to this receiver we're calling A1, which is great. So now we know what's going in, and we can characterize that. But with any mismatch, anything less than perfect in terms of the connection impedance or the characteristic impedance of the two connections is going to induce a reflection. So we want to be able to characterize that reflection also. So we do that by adding a coupler, flip the other direction. In this case, we're measuring the return signal coming back from that, and that's sent to receiver B1. And this gives us the scattering parameter, or S parameter, known as S11. And the way that's read is it's the scattering parameter seen at port 1 from port 1, which is actually the ratio of the B receiver over the A receiver into our device under test. So now that doesn't yet tell us anything about the performance of our device under test, only how much of the signal is being reflected. So next, we need to see how much of the incident signal is transmitted. So in order to do that, we use the same scheme with the forward transmission coupler into a receiver. In this case, we're going to call it B2, and this will give us our S21 parameter, which would be your forward forward direction, which is again the ratio of the B1 receiver measurement over the A1 receiver. So it's how much is coming out over how much is going in, or scattering parameter S2 seen from port. Seen from port 2, measured from port 2, seen from coming from port 1. So the next step is we're trying to determine how much of this, if this is a reciprocal device, how much of this device under test provides a reflection on the output port. So in order to do that, we need a signal to be coming from this direction. So the way that's handled in the network analyzer is to put a switch from the source and route the signal this direction. It's then coupled with the other receiver, and the A2 receiver, and the reflection is measured on the B2 receiver. So that will provide your S22, I get that right, which is your B2 over A2 measurement. And then the reverse of that is true on the S12. So we refer to this as the forward direction and the reverse direction, and the port 1 reference plane and the port 2 reference plane. And when we say reference plane, that's typically where we're defining where the calibrated measurements start. Okay, and with the new designations, we have switched to the capital letters, like I mentioned. So we call this the A receiver and the R1 receiver, and the B receiver and the R2 receiver. So the current measurements are as follows. So your S21 is going to be your B over R1. And this will become important when we get to the demo section coming up. So in quick summary of S parameters, your S11 is your forward reflection coefficient, or your match, and your S22 is your output match. Your S21 is the gain or loss, depending on your device or your terminology, and then the isolation is measured by S21. And just to note, S parameters are inherently complex linear quantities, meaning magnitude and phase, but they're often expressed in log format just for to be able to view the scale better. Okay, so putting all that together, what does a network analyzer actually look like? This is what it looked like a long time ago. And we put this picture here because it lines up with the block diagram pretty interestingly. So we had a source, which in this case is the unit down here. And then a signal separation device, the couplers and bridges and whatnot, used to pick off and measure the signal, and then those are over here where the cable section is. And then that information is piped to the receiver detector and then to the processor display. So if we align that to this device, it's actually the block diagram turned upside down is actually how this is laid out. Nowadays, we put them all in one box, and we add a lot more bells and whistles. But the fundamental basics of the network analyzer are still the same, just better. So your 2-port network analyzer, this is the form of the block diagram that you'll see in our documentation and the simplest example. So the source and this, you can see the source and the switches between the direction and the couplers and receivers that we talked about previously. And the reason that I mentioned we had to switch between the notations is when you get to higher port count analyzers, such as a 4-port analyzer, this would get more and more confusing. So this way you can use your subscripts to indicate which receiver is tied to which port. And there are other configurations where we can use modular network analyzers where we can have 50 ports. And so the block diagram gets pretty complex. Okay, some additional options that we now include, that are now included in modern VNAs, are different switching options, different switching paths, LNA receivers, attenuators, and bias tees to control and measure your additional equipment. A couple more things to mention before we dive into the demo. In the receiver display processor, we can do all these different measurements with the math on the actual traces. So we'll get to that in a moment. And here's just a shot of what the modular VNAs can look like in some cases, where you can have one device under test with a multitude of signals all pumped into a multi-port VNA. Okay, so rather than go through slides here, I think what we'll do is I'll actually pull up a network analyzer. Okay, and get this out of the way. You guys should be able to see the network analyzer screen. This is the default
Hey,
measurement.
Jason, before we start the demo, there's a couple follow-up questions that I want to address before people have to leave at 3 potentially.
Okay,
This
sure,
is from the connectors.
sure.
So this is a follow-up. Yeah, James, I don't know if you can see the chat.
Maybe if I can find it.
Yeah. So we had a follow-up question to the labeling connector question.
Okay. So that's from James. Oh, weatherproofing cables and a highly corrosive. Let's see. I'm not sure on a highly corrosive environment. The weatherproofing I don't know on that one. I know in the cellular world they use that it's like an asphalt that is pretty destructive to the outside of the connector, but it does keep it safe. You just can't mess with it. But that is one for the cabler manufacturer. I'm not sure, so I'll have to pass on that one. And James's question, for those who already have their inventory of connectors and which to identify the endpoints with labels, what sound like, I'm sorry, wait, already have their inventory of connectors, which to identify the endpoints and labels sounds like recommendation is not to do. I'm sorry, I'm not understanding that question exactly. Which to identify the endpoints with labels. I mean, I think the labels, there's no right or wrong. I think there's just there's a standard that, like I mentioned, Maori was trying to push. I think it's an an open labeling standard, but you can do whatever you like as long as you don't damage as long as you don't mess with the open end of the connector. Anything on the outside of any labeling on the outside of the connector would do no harm to the measurement.
Okay, yeah, and if we have further details, we can go ahead and send an email out to as well.
Okay. Yeah, here we'll jump back to the network analysis real quick, as I don't want to keep people past time. The default setup. So we're just going to jump to a quick start. This gives us all 4 S parameters. I can see that this device is only good to about 5 gigahertz, so we'll just set the stop frequency there. And now we can just see S11, so that's seen at port 1 from port 1, and then S12, so seen at port 1 from port 2, and the reverse of those. So you can see that the signal is passing some energy in the middle and reflecting energy on the outer edges. So this is what a bandpass filter looks like through a network analyzer. And we haven't got any calibration, but that would, the typical path here is to pre-test your device under test to make sure you have your setup right. So we usually hook it up and take a look at it, knowing some idea what the power level is like and knowing that it's safe to do. Plug it in and take a look at it, and then get everything all set up. Get your frequency, get your number of points set up, and get everything all like it before we proceed on to the calibration. The calibration will be you can done automatically through the calibration menu, or we can break it up into a separate course if we actually get into the math of the 12-term error correction for calibration. So we don't have time to get into that today, but just note that that's later on down the chain, and I haven't forgotten to do it. It's just haven't got there yet. But anyway, what I wanted to show is if we have our S21 measurement, if we wanted to figure out how that S21 measurement is how we come up with that measurement, what we're going to do is refer back to our equations. And if we were to add the S21, which is going to be our B1 receiver and our R1 receiver, we get those traces on there. Now, if I did a new trace and some math. Now, if I did some math here and I did my B1 trace, which is trace 5, and I divided it by my R1 trace, which is trace 6, that will equal my S21. So you can see the S21 and, sorry, let's get rid of that one. Where'd S21 go? S21. Yeah, you can see that they overlay identically, as they should. Oh. Okay, so that's just the fundamental derivations of how that works and a quick crash course in how to demonstrate that. And that can be done identically for the other S parameters. So with that being said, are there any other questions? We have 3 minutes left.
Real quick before people start to head out, I'm gonna launch this quick poll just to see if there's any further needs of the group, and I can stay after for questions, Jason. I don't know if you have anything after, but we can go a little bit over, and if you guys are welcome to stay as well, if there's no other obligation you have, Jason.
Yeah, sure. I'm willing to stay. I just wanted to give an opportunity to ask questions.
Yep.
I think it's probably not a good idea to get started on any more topics, just because I think they all go pretty deep. So either did I miss anything that you think of? Have
I think we
lots
did
of
a good job bringing up the basics, and we can always put on further seminars like I mentioned. Once you guys leave the meeting, there's going to be an evaluation, and if there's something you guys want to hear more about, please put that topic in there, and um, we can do something in the future, and yeah.
Okay.
Okay, I'm gonna close this poll real quick, and then again, feel free to ask questions, but we'll be sticking around.
Okay. Yeah, I when you close the poll, I pulled up a screen just showing some of the markers um, of a similar filter, just to show how that may look. Let's see. So I literally have over 100 slides on this topic alone, and in 30 minutes we got through about 20 of them. So there was much more to cover in future sessions. I didn't want to do it all in once, save some stuff for the future sessions. All right, well, I don't see any questions. So I guess I've completed that for now.
Yeah,
Great job
thank you
with
so
the
much,
math,
guys.
Jason.
Yeah.
Yeah, I need to go outside and get some fresh air.
Yeah, thank you all for joining, and you guys were a great audience to have. And please, again, if you have any questions, please, feel free to jump in. And one thing I want to mention is, as Jason said before, we can only do so much in this hour, but Jason did a great job of getting to the basics and just opening the door to further topics that we could expand upon. And like you said before, Dr. Joel's book on network analysis, I think we talked about this before. It's over 800 pages, and to fit it into a half an hour, that's pretty ambitious. So, but thank you guys for bearing with us. We had a great time. And again, if you guys want to see more of a certain topic, please put in the evaluation. And yeah, we're gonna have another part to this Back to Basics series next week on Tuesday, I believe the 17th. That's spectrum analysis basics. Jason will also be part of that as well. He'll be presenting. So I look forward to seeing you guys there as well. And thank you for joining us. We'll stick around if there's any more questions, and yeah.
Yeah, and sorry to James, I didn't have the answer to your question. Um, so it looked like we had a pretty decent turnout. Some names I recognize, so that's good news. I guess that's the benefit to doing the remote webinar is that we can have a broader reach.
Right, that is, yeah, we've got people on both coasts here.
But no pizza. That's
No pizza with pineapple.
yeah.
That's right.
Well,
Most of us don't want that, so.
if we did this in person, this would be the point when I can scarf down pizza. Now I'm
Yeah.
done. Now I can eat.
What was
And
it? 60% said yes to pineapple and 30% said no. So,
Yeah.
or so 60% said no. So we can have 30% of the pie with pineapple and 60% without it, and then the rest of it will be something else.
Well, it doesn't look like we have any more questions, so I'm going
Yep.
to end the training so we can get the recording downloaded and I can get that out to everybody.
oh
Awesome.
boy,
All right.
Yeah. Thank you guys so much again, and hopefully we'll see you guys next week.
Thank you. Bye.
thank you.
Bye.